This is Module 31 of Engineering Vibrations 1, an Introduction to Single Degree of Freedom Systems. Today we're going to wrap up with the transient response of single degree of freedom systems undergoing free vibrations with damping. This time we're going to look at critically damped systems. And so we've looked at undamped, underdamped. Last module we looked at overdamped, and here we finish up with the critically damped system. And so there's our roots. We rewrote them to look like this. If zeta equals 1 for critical damping, then the argument underneath the square root sign goes to 0, and we end up with two negative repeated roots, minus omega natural. And so lambda 1 and lambda 2 are minus omega natural. We substitute those back into our assumed solution. And if you remember from your math, and you can go back and review your math for solving differential equations, that when you have repeated roots, the second term is multiplied by t, as we've shown here. Then we apply the initial conditions to find A3 and A4, as we've done before, and this is the final response. Y0 minus omega natural t plus the quantity y0 omega natural plus y dot 0, the initial velocity, all times t to the times e to the minus omega natural t. And this is indeed the fastest return to equilibrium with no overshoot. And we saw last time the overdamped case where with the door video, the larger the zeta, the slower the return to equilibrium. Well, when zeta goes down, last time I showed a graph with 1.4. Now if it's 1, it goes down as quick as possible to the equilibrium position, which for the door is the closed position without overshoot. And so I've given you a worksheet here to work a problem with critical damping. This is a Cannon. Even modern day howitzers and have damping recoil systems. And this is just an illustration of an older one. But the Cannon, which we're saying weighs 1,200 pounds, shoots a 100-pound cannonball at a velocity of 600 feet per second. The Cannon then immediately comes into contact with a spring stiffness of 149 pounds-feet and a dashpot that's set up to critically damp the system. Assuming that there's no friction between the wheels and the plane, find the displacement toward the wall after 1/2 second has elapsed. And so that kind of puts things all together. I've put the solution in the module, and when you finish that, you should have a very good grasp of critically damped system. So that sums things up for this module. We solved transient response of single degree of freedom systems undergoing free vibrations, and this time experienced critically damped conditions. And so that wraps it up for this module.